Every time a passenger plane leaves the runway, something incredible happens. A machine weighing hundreds of tons defies gravity, climbing higher and higher into the sky. But the real miracle isn't the airplane itself. It's hidden beneath the wings, a pair of giant engines, each one powerful enough to produce more than 100,000 pounds of thrust, spinning thousands of times every minute while surviving temperatures hotter than molten lava. Yet these engines must perform perfectly for thousands of flights, because even the smallest mistake could put hundreds of lives at risk. So how do engineers build one of the most powerful and precise machines ever created? How can thousands of individual parts fit together with microscopic accuracy? Why do some turbine blades cost more than a luxury car? And how can an engine generate enough power to lift an entire aircraft? Across oceans today, we are going inside one of the world's most advanced aerospace factories to discover how modern jet engines are made. The journey begins not inside a factory, but inside a design laboratory. Long before a single part is manufactured, engineers spend years designing every component. Using powerful supercomputers, they create detailed three-dimensional models of the entire engine. Every blade, every bearing, every bolt, every fuel nozzle exists inside a virtual world before the real engine is ever built. Then the simulations begin. Engineers test extreme temperatures, violent vibrations, massive air pressure, bird strikes, heavy rain, lightning, ice formation, and thousands of flight cycles. If even one component shows weakness, the design is changed again and again. Only after millions of digital calculations does manufacturing finally begin. But building a jet engine is unlike building almost anything else, because some components must survive temperatures exceeding 1,700 degrees Celsius, hotter than the melting point of the metal itself. This challenge has pushed engineers to develop some of the most advanced materials ever created. Without them, modern aviation would simply not exist. Now the raw materials arrive, but ordinary steel is not enough. Jet engines are built using titanium, nickel-based superalloys, and advanced composites. These materials are chosen not only for their strength but also for their ability to survive extreme heat, enormous pressure, and constant vibration. One of the most valuable components is the turbine blade. It may look small, but it is an engineering masterpiece. Each blade must withstand temperatures hotter than the surface of molten lava, yet it cannot lose its shape or strength to manufacture them. Molten superalloy is poured into precision ceramic molds using an advanced process known as investment casting. Some of the most advanced blades are even grown as a single crystal without any grain boundaries, making them far stronger than ordinary metal. Tiny cooling channels are built inside each blade. These microscopic passages allow cooler air to flow through the blade, keeping it from melting even while the engine operates at full power. This technology is one of the greatest achievements in modern aerospace engineering. Once the turbine blades are complete, the next challenge begins: precision machining. Every rotating part must be almost perfect, not within millimeters, not within micrometers, but within tiny fractions of a millimeter. Computer-controlled CNC machines shape the compressor discs, shafts, bearings, and turbine components, removing only the exact amount of material needed. Powerful lasers and optical scanners measure every surface. If a component is even slightly incorrect, it is rejected, because at full power the engine can spin more than 10,000 revolutions per minute. At those speeds, the smallest imbalance could create massive vibrations or even destroy the engine. After machining, engineers begin the balancing process. Each rotating assembly is placed inside special balancing machines. High-speed sensors detect the tiniest weight differences. Engineers carefully remove or adjust microscopic amounts of material until the entire rotor spins with near-perfect balance. This precision is one reason why modern jet engines can operate for thousands of flight hours With incredible reliability now, assembly begins inside a spotless engine factory. Everything must remain exceptionally clean because even a tiny particle of dust can damage critical components. Engineers carefully install the massive fan, the largest part of the engine. On some engines, the fan diameter is wider than the height of an average person. Its lightweight titanium or carbon fiber blades are designed to move an enormous volume of air. Surprisingly, most of the engine's thrust doesn't come from burning fuel. It comes from this giant fan. As it spins, it pushes huge amounts of air around the engine core. This is called a high bypass turbofan engine, making modern aircraft far quieter, far more efficient, and far more powerful than older engines. Behind the fan, engineers install the compressor stages, then the combustion chamber, followed by the turbine. Finally, the exhaust nozzle. Each section must align perfectly with tolerances measured in microns. Once assembled, thousands of sensors are connected, monitoring temperature, pressure, fuel flow, oil systems, vibration, and engine health. Only then does the engine begin to resemble the incredible machine that will soon carry millions of passengers across the world. But building the engine is only half the journey. Before it is allowed to power a passenger aircraft, it must survive some of the toughest tests in engineering. The completed engine is mounted inside a massive test cell built with walls thick enough to withstand its enormous power. Engineers connect hundreds of sensors, monitoring every detail: fuel pressure, airflow, oil temperature, vibration, exhaust gases, and thousands of other measurements. Then, for the first time, the engine comes alive. Fuel ignites, the compressor begins spinning. Within seconds, the giant fan accelerates to incredible speed. A thunderous roar fills the test facility. As thrust increases, the engine produces enough power to move a fully loaded passenger aircraft. But engineers don't stop there. They simulate extreme conditions: heavy rain, freezing temperatures, crosswinds, and even bird strikes. Special tests fire large birds into the running engine to prove it can continue operating safely. Other tests throw ice, hail, and water into the intake. The engine must keep running without catastrophic failure. Only after passing thousands of hours of testing does it earn certification, ready to fly, ready to carry millions of people safely across the skies. Every time a jet engine starts at an airport, you're witnessing one of the greatest engineering achievements in human history. A machine built from thousands of precision-made parts designed to survive extreme heat, incredible pressure, and years of continuous operation. Yet it performs its job so reliably that millions of passengers trust it without a second thought. Behind every successful flight stand thousands of engineers, designers, scientists, technicians, and factory workers whose innovation makes modern aviation possible. From a block of metal to one of the most powerful machines ever created, the journey of a jet engine is a story of precision, innovation, and relentless engineering. The next time you hear the deep roar of an aircraft taking off, remember, you're not just listening to an engine, you're hearing decades of scientific progress, millions of hours of engineering, and one of humanity's greatest inventions. If you enjoyed this documentary, don't forget to like, share, and subscribe, because here on RailForge we explore the world's greatest engineering marvels, mega factories, aerospace technology, modern transportation, and the incredible machines shaping our future. Thanks for watching, and we'll see you in the next engineering documentary.